Alright, hello, I'm Dr. AJ Kumar, PhD. Go away, OBS. Where did I put the physical book? Because we need that a lot. Physical book. There it is. Okay. So, I think I'm going to do, this is what I do if I'm reading a real book. Is go through, I did this a little bit on the last video, but go through, what the fuck? There will be a link to buy this down below. Please go buy the physical book. So what I'm going to do, I'm going to get the highlighter. Okay, and I'm just going to highlight the terms. Okay, homomorphism, there's a term. Let's see. 2.5.1. Okay, let's go through and look for terms and highlight those first. Trivial homomorphism. Okay, I know what that means. That's a terrible highlighting job. Inclusion map, I know what that means. Let's see. Image of a homomorphism. Kernel of a homomorphism. Alternating group. God damn it. Okay, I need to make this smaller, sorry. Alternating group. I know what that is. Left coset. Okay, I know what that means. Let's see. Conjugate. Normal subgroup. What that means, this is an important term. I'm gonna put a star next to this because this is an important term. We want it to be the navy blue. Star next to this. This is an important term. It's a terrible star. Oh well. Oh, I have my thing at an angle. That's the problem. God damn it. I hate computers so much. Okay. Just looking. Center of a group. I don't remember. Yeah, okay, yeah, it's the things that commute with everything. Oh, it's easier to highlight with my mouse than with the pointer. That pi notation, okay. And now we're going to go back with bright blue and highlight all the references to prior sections. Okay. So I do highlighting the terms, and so that way in my head I hear the terms before I go read them. So I'm like, okay, and see which ones I know. Okay, I remember all of them. Center, I don't quite remember what that means, but then I looked, I'm like, oh yeah, duh, I remember that. I remember hearing the term before, I don't remember what it meant. Okay, so, okay, 2.5.1, but that's just on the previous page. Should I bother with that? Yeah, why not? Yeah, I'm just going to highlight them for now and then go back and do, maybe I'll write down, 251, 223, that's going to be important. Boy, that's bad. I'm going to make it bigger. And I'm probably going to miss some. I'm just scanning really quickly with my eye. 2 to 11. Here we are. Two, 5, 8. That's on the previous page. Yeah, I'm not going to do the ones on the previous page, actually. 227. Okay. I think this is the usual presentation of S3, which I can try to remember. But see, the reason I do this highlighting is because 227. Oh, that's right. That was. And then I kind of scan nearby. Oh, it's the usual presentation of S3, and we did that in the last video, so I can kind of remember what that is. Let me make sure I'm recording with the right microphone. I am. Okay. Okay, this chair is just murdering my posture, so I'm going to move the desk to standing position. Because I can just feel like my neck muscles getting weaker as I'm sitting in the chair. So if I'm working for a long period of time, maybe I'll do that, but alright. Let's go. Okay. Homomorphism. Isomorphism. Okay, so that's the end of the section. So we're only going to read one section. Okay. Okay, and so let me look in the physical book. Okay, and I'm going to erase this because we don't need this one that's just for the previous. Okay, there we go. Okay. So 223, let me look that up. 2.2.3. That's the Group Cancellation Law, okay? This is the Group Cancellation Law. This is the logic of, if AB equals AC, then B is equal to C. That's the logic behind that. That's what that means. I don't prefer to think of, oh, this theorem, that theorem, that theorem, that theorem. I prefer to think of, well, the logic. I try to remember the logic rather than the conclusion. But in some sense, the conclusion is sort of a rewrite barrier, if that makes sense. Oh, that's actually kind of an interesting context in which the idea of a rewrite. This is an important idea in entropism, which is my episteme I'm making. One of the most important ideas is called a rewrite barrier. Or a rewrite boundary. And I just realized a theorem is a rewrite barrier over some logic. Read Revelations 20 that'd be Revelations 22. And I'm going to get my website up pretty soon. That's on the OPHTTP playlist. OPHTTPD playlist. Boundary. And then it'll have a list to all my revelations. Barrier over some logic. In the same way that a function when you call a function, it's invoking a procedure. When you call a theorem, it's invoking some logic. Okay. To obtain phi of 1 is equal to 1. Okay, just, what page is that on? 41. And it's possible that the PDF is from a different edition than my book, but so far they seem to match. Okay, and then 2.2.11, that is page 43. And what is that? That's the definition of SLN. But I know what that is. It's the matrices with determinant 1, okay. Oh, and it's the idea that a determinant is a homomorphism. That's interesting. There's one more, I think. Yeah, 227. 227. That's S3. That's the definition of S3. So 227, that's usual presentation of S3. I told you that usual presentation was a term. Of S3, which, let me try to remember it. It is 1x squared, and I remember because x has order 3, and then y has order 2, so you can't go to y squared. And then you multiply on the left by xy, and then I think x squared y. And those are all the possible terms because S3 has order 6. So I think that's correct. Is that correct? It is. Okay. All right, let's go back and get to reading. Okay. Now I have to pee. So it's not a very long section, so we can just read it, I think, all the way through. Okay, let G and G prime be groups written in multiplicative notation and homomorphism. A homomorphism phi from G to G prime is a map from G to G prime. Just trying to adjust my monitor. I need to go get a level because I keep thinking. Okay, glasses. A homomorphism is a map from G. No, those are not helping me. That prescription is like 3 years old, and so it's not making me better. Anyways, a map from G to G prime such that for all A, B, and G, phi of AB is phi of A times phi of B. The left side of this equation means first multiply A, B, and G, and then send the product to G prime using the map phi. So we have A, B, composition in G. Okay, I'm going to use a thinner marker. G. Is there a way to draw straight lines? Not easily, okay. Compose in G to get AB, and then phi from G to G prime to get phi of AB. Okay. And then we have A, B, I should have started. Okay. Okay, I know what I'm going to do. Phi G to G prime. Just writing this down. Phi G to G prime. Okay, phi of A, phi of A, B, compose in G prime in G prime. Okay, and that'll give us phi of A times phi of B, and then the claim is that these two are equal. That's how you dissect that equation. Okay. Yeah. Correct. Okay. Intuitive. That's right. Intuitively, a homomorphism is a map that is compatible. That's like, this is a quasi-term. I'm going to put that in brackets as in braces, as in that's some kind of a term. Provides a way to relate different groups. Okay. Examples 2.5.2. The following maps I'm just stretching, sorry. My neck muscles feel weird. The following maps are homomorphisms. The determinant function, right, so this is reflective, the fact that it's a homomorphism. 1.4.10, I should have, okay, fine. Okay, I'm going to highlight this because I missed it. The exponent, is there anything else? Okay. I'm not going to go back, I'm not going to interrupt the reading just to go back and do that. But this is reflective of the fact that the determinant of A times B is equal to the determinant of A times the determinant of B. And it's important to note that these are different operations. So this is matrix multiplication, this is scalar multiplication over here, right? So this is lovely. Math is C++ minus the constraint that it has to compile because it's using different operations. Implicit context swaps, that's mathematics that's the bread and butter of mathematical notation. Implicit context swaps. Mathematicians think this is really clever. That's why I'm saying the mathematics is super susceptible to this postmodern wokeism nonsense, because they just love this word games, implicit context swaps, all this bullshit. Anyway, the sign homomorphism sends a permutation. Yeah, because the sign, right, so the sign of the composition of p prime times p, let's say, this is equal to the sign of, this is composition of permutations over here is the sign of p prime times the sign of p, right? So go check 1.5.11. Can I? I'm not going to go. Go look yourself in your book. Exponential map. Right, so this is reflective of the fact that the exponential, because it's going from the additive group to the multiplicative group, this is reflective of the exponential of a plus b being the exponential of a times the exponential b. See, if you want more about this, check Revelation 6. I'll try to remember to link that. Let me actually, this is AA25 links. Okay, Revelations 22, that's super incomplete, but, and then Revelation 6, and then Glowy Math 1. I saw another video, I saw another channel do this where he had, it was that weird weird little Russian dude with the translucent skin that does great programming videos. Soding, I think is his name. His videos are excellent, and he looks like a ghost. see, the map z plus to g. Yeah, okay, so where a is a given element, so maybe phi sub a would be better. Phi sub a, okay? Okay, but this is a homomorphism because, and z plus means that, does not mean positive integers, it means the additive group of integers. Oh, and wanted to also add Rudin, real, and because that's what I'm reading in Glowy Math 1, and also Rudin, Principles of Mathematical Analysis. I gotta go finish my deep, because I did like a really shallow dive in that video. Okay, anyway, phi a, okay. Okay, and so this is reflective of the fact that phi a, okay, of n plus m is equal to a to the n times a to the m, or which is a to the n plus m. So by definition, phi a of n plus m is a to the n plus m, which is equal to a to the n a to the m, which is equal to phi a of n times phi a of m. Okay. And then the absolute value map. So what this is saying, this is a reflective of the fact, okay. This is reflective of the fact, so what this is saying is that, okay, here's an easier fact to prove. That with the complex numbers, if you have z and w are complex numbers, okay, then the quadrants of z times w, quadrants is just absolute value squared, but I prefer to think of absolute value as the square root of the quadrants, because it's very easy to prove that the quadrants of z times w is the quadrants of z times the quadrants of w. You write out z times w, you write out quadrants of z, quadrants of w, take the, it's just straightforward algebra. Okay, and then you take the square root of both sides and you get the fact, yeah, that, yes, this is reflective of this. Okay, the examples C and D, the law of composition is written additively in the domain and multiplicatively in the range. The condition to, okay, sure. The formula showing that the x, yeah, okay, I just said that. Okay, the following homomorphisms need to be mentioned, though they are less interesting. The trivial homomorphism, yeah, it just sends everything to the identity, because that's trivially a homomorphism, because, right, the identity times the identity is the identity, so it works with the composition rule. If H is a subgroup of G, the inclusion map is a homomorphism, okay. Let phi from G to G prime be a group homomorphism. If A1 up to AK are elements of G, then phi of A1 up to AK, right, this is just the associative property. This maps the, yeah, it has to, just by the okay, yeah. Yeah, this is a proposition, okay. So this is inherited from associativity, this is forced by the definition of identity. Inverses to, yeah, that's forced by the definition of inverses, okay. The first assertion follows it's just forced by associativity. Next, 1 times 1 is equal to 1. Right, so by the... okay, so maybe phi of 1 sub G, 1 sub G, 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 okay, to phi of 1 sub G is 1 sub G, prime. That looks like an S, but I meant G. Yeah, okay, yeah. He uses my notation here. Okay. A inverse, right, okay. Phi of A inverse is the inverse of phi, okay, right. Another group homomorphism determines, or a group homomorphism determines two important subgroups, its image and its kernel. This is, in a sense, this is a hint of what I call that fundamental theorem in mathematics. I talked about it in AA 21. You remember to link that. I also hint at it in Revelations 8, which is super incomplete, but it's a draft that's there. The image of a homomorphism is the image as a map of sets, okay? So, image of phi is the set of x and g prime such that x is phi of a for some a in. Okay. Another notation for the image would be phi of g. This is the more common notation. Okay. How long is this chapter? I just wanted to check. 49. Okay, we got 2.5 more pages. Okay. The image of the map z plus to g that sends n to a to the n is the cyclic subgroup, right, okay. The image of a homomorphism is a subgroup of the range. Of the range of the function, so the image of the function. Okay. The range? See, this is one of those glowy terms that means something different to every mathematician. Range. I'm going to highlight that as a glowy term. Okay. I think he means codomain. That's the more standard term. Or target space. We will verify closure and omit the other verifications. Let x and y be elements of the image. Since phi, okay. So xy is equal to phi of something. Okay, so yeah, so the image is a group for precisely this logic right here. Or at least that it's closed. It has the identity and then it has inverses because of above. Okay, yeah. The kernel of a homomorphism is more subtle and also more important, right? The kernel of phi, often denoted by kernel of phi, okay, is the set of elements of G that are mapped to the identity in G prime. Yes, so it's the pre-image of the identity. So it's everything. So we have G over here. We have, I'm going to make G prime really big. Then we have 1 in G prime. And everything over here that maps to 1, this is the kernel. Okay, right. The kernel is a subgroup, right, because it's closed. Okay, yeah. The kernel of the determinant homomorphism is the special linear group. Right, it's everything that goes to 1. The kernel of the sign homomorphism is the alternating group. It's even permutations denoted by an. Okay, yeah. The kernel is important because it controls the entire homomorphism. How do you figure? Tells us not only which elements of G are mapped to the identity in G prime, but also which pairs of elements have the same image in G prime. Let me read that again. It controls the entire homomorphism. That's quite an interesting claim. Controls the entire homomorphism. I'm going to mark that in red. How about that? Controls the entire homomorphism. It tells us not only, god damn it, which elements of G are mapped to the identity in G prime, but also which pairs of elements have the same image in G prime. Oh, okay, yeah. Okay, he's going to elaborate on this in a minute. Okay, I think that makes sense. Okay. If H is a subgroup of a group G and A is an element of G, the notation AH will just stand for the product of all elements AH with H and H, right? Correct. Okay, this is a left coset. Okay, this is annoying, but yeah, left coset because the element is on the left. Okay, let me write this. Yeah, left coset. This is glowy term, so it goes in green. Equals element goes on left. The left. Okay. Let phi from G to G prime be a homomorphism of groups, and let A and B be elements of G. Let K be the kernel of phi. The following are equivalent. Phi of A is equal to phi of B. A inverse B is in K. So I can see how this implies this. Okay. Right, because you multiply, yeah. And I can kind of see how if A inverse B, okay, yeah, you multiply by phi of A inverse on this side. Yeah, okay, so I can see how you get between these two. B is in the coset AK. How do you figure this? So I can see how A inverse B is in K. Right, so if A inverse B is in K, then B is equal to A times A inverse B then B is equal to A times A inverse B. Right. Okay. So I understand how this implies this. Okay. The cosets BK and AK are equal. BK and AK are equal. So maybe we can, how do we get from B is in the coset AK to A inverse B is in K? Let's think about that. Okay, so if B is in AK, let's start with B is in AK. Then there is big K. Then there exists some K where AK is equal to B. That's what that means. And so K is equal to, little k is equal to A inverse B. Duh. Okay, yeah, so I can see how this implies this. Okay. The cosets BK and AK are equal. So I guess the way to show that is if, so let's suppose the cosets are equal. Okay, so maybe we use the fact that it's the kernel of a homomorphism. the cosets bk and ak are equal, okay, okay. So if B is in the coset AK, then A inverse B is in K. But since K is a subgroup, then it also contains, here's a way to do it, okay? So if B is in AK, and then the logic is completely symmetrical, what we can use is the fact, this means that A inverse B is in K. But since K is a subgroup, the inverse of this, so this implies that B inverse A, which is the inverse of this, is also in K. Okay, but by the logic we just did, this implies that A is in BK. Okay. And then you can just play this logic in reverse. So and you get A is in BK if and only if. Because A is in BK, that implies B inverse A is in K. Right, you can just play the logic in the reverse. I don't need to read the proof. Or maybe I read the proof to see. Sometimes it's useful to read the proof to see if I missed any details. Okay. But I understand this logic. Okay, and then, and then we want to prove that this is equivalent. So if AK and BK are equal, the cosets are equal. That's something I have difficulty with, but the cosets AK and BK are equal. Okay. So let's consider if the cosets AK and BK are equal and K is the kernel of a homomorphism, then I can see, so if AK equals BK, big K, then what we're going to do is we're going to take the image of these two under phi. Okay, so phi of AK. So this is a whole set. So this is phi of A times phi of K. So we're being glowy-ish with our notation, but this is a set. This is a set. This is the image of a set. This is an element times the image of a set. Okay? We're being glowy-ish with the notation, but okay. But this is equal to simply the element 1. Okay. So here, let me rewrite it this way. Okay. AK is the set of all AK where little k is in big K, sorry. Okay. Phi of AK, god damn it, is the set of all, well, phi of a little k where little k is in big K. Okay? But this is equal to the set, this is just equal to phi of A. Okay, the reason for that is, okay, let me just show you. Phi of A times phi of K where little k is in big K, but by definition, phi of little k will always be equal to 1, so this is just the singleton set phi of A, okay? And by the same logic, if we just apply this to B, because using the fact that k is the kernel of phi, this is equal to phi of B, okay? And this is a set now. The set phi of B, okay? So we know that the set containing phi of A is equal to the set containing phi of B. Therefore, we know this implication, and now we have a cycle of implications. Okay. Okay. So let's just read Artin's proof. Suppose that phi of A is equal to phi of B, then phi of A inverse B is equal to, you split up using the homomorphism, phi of A, yeah, because these two are equivalent, so phi of A equals phi of B, so it's phi of B inverse times phi of B, which is equal to 1. So therefore A inverse B is in the kernel of K. To prove the converse, we turn this argument around. If A inverse B is in K, then 1 is equal to phi of A inverse. Yeah, and so then you have 1 is phi of A inverse B, so you multiply by phi of A inverse, so you get phi of A is equal to phi of B. This shows that the first two bullets are equivalent. Okay, their equivalence with the other bullets follows, but okay, so I had to prove it, he didn't prove it. Okay, a homomorphism is injective if and only if its kernel is the trivial subgroup. I can see how so injective would mean phi of A, this is the equals phi of B implies A equals B, okay? Okay, so if we have this is our definition of injective. So suppose it's injective, and we know there are two elements, phi of A and phi of B, such that A is equal to B. Okay, so if we know it's injective, well, if we know if it's injective, then obviously there's only one possible thing that can go to the kernel, and that has to be trivially 1. Okay, so injective implies kernel trivial. That's easy, okay. But if the kernel is trivial, let's prove that it's injective. Okay, so if the kernel is trivial, okay, so suppose the kernel is equal to 1, and we know that there are phi of A equals phi of B, and our goal is to show that A is equal to B. Well, by the logic we just did, this implies that our goal, we know this, and we're trying to prove A is equal to B. Well, we know A inverse B is in the kernel, and A inverse B is equal to 1. So then we can conclude that A is equal to B. Okay, so we're good. Okay. He just proves it. Yeah, okay. The kernel of a homomorphism has another important property. If A and G are elements of a group G, the element gag inverse is called the conjugate of A by G. Okay? A subgroup N of a group G is a normal subgroup if it's closed under conjugation. If for every A in N and every G in G, the conjugate GAG inverse is in N, is in a normal subgroup if for every A in N, okay, for every and for every, okay, the kernel is normal. If A is in the kernel of a A is in the kernel of a homomorphism, then right. So first, to prove that the kernel is a normal subgroup, that's important. And then I think, and then when we get to quotienting, we'll see that every normal subgroup, you can construct a homomorphism. So subgroup is normal if and only if it is the kernel of some homomorphism. Okay, that makes sense. But you need to talk about quotienting before you can establish the other direction of that. Thus, the special linear group is a normal subgroup of the general linear group, and the alternating group, right, because they're kernels of homomorphisms. Yes, okay. Every subgroup of an abelian group is normal because commutativity. Subgroups of non-abelian groups needn't be normal. With its usual presentation, the cyclic subgroup Y of order 2 is not normal because Y of G, because Y is in G, but xyx inverse is equal to x squared y. So what is, let's verify this. Okay, so 2.2.7. So we have this rule. Okay, so can we conclude? Okay, we know yx is equal to x squared y. Right, so we know we know x inverse is equal to x squared. That might be it. Do we know that? Yeah. So we know x inverse is equal to x squared. So xyx squared, because x cubed is equal to 1, is equal to, we know yx is equal to x squared y. So this is x squared, x to the third x times x. Okay, which is equal to yx, which is equal to x squared y. Okay. Okay, what is y? Yeah, so x is 1, 2, 3, and y is 1, 2. So, yeah, so y is its own inverse, right? Yeah. Okay, and then what is x squared? What is, let's do y. Let's do x squared y, or yx, is equal to 1, 2 times 1, 2, 3. Okay, and so this is 1 goes to 2, which goes to 1, so 1 is on its own. 1 goes to 2, 2 goes to 1. 2 goes to 3 and is left alone. 3 goes to 1, which goes back to 2. Okay. So this is 2, 3. Okay. The center of a group, which is often denoted by Z, is the set of elements that commute with every other element. Z and G, such that Zx is equal to Xz for all X and G. A center, okay. It is always, okay, yeah, because ZX inverse is equal to X, right. That's interesting. The center of the special linear group SL2 of R is just those two matrices. Wow. Okay. The center of the symmetric group Sn is trivial if n is greater than or equal to 3. Okay, I don't know how to prove that, but is trivial. This is an important fact and I don't know how to prove it, so I'm going to put it in. Should I put it in glowy green or put it in red? Red's better. Red is better. Save my work. Okay. Oh, we're almost done. A homomorphism, example of a homomorphism from S4 to S3 between symmetric groups. There are 3 ways to partition the set of 4 indices into pairs of subsets of order 2. This is combinatorics, which I don't remember. Pi 1. Okay. An element of the symmetric group permutes the 4 indices. And by doing so, so, right, if you permute the 4 indices, you map to one of the, okay. I'm not going to verify that, but that makes sense. Okay, and so S4, how many elements are there? There's going to be 24 elements. There's 24 possible there's 24 possible 24 possible permutations, but only 3 possible, okay. Okay, so you pick one to go to one of the partitions, and then you only have 3 choices. Okay, that makes sense. And so you don't care about order within, okay, so some combinatorics nonsense. I got to brush up on my combinatorics. This defines the map, phi, from S4 to the group of permutations of the set pi 1, pi 2, pi 3, which is the symmetric group S3. So it's really determined by where 2 goes, it looks like. So if 2, so 2 has 3 choices of where to go. If 2 goes to 1, you're stuck in the first partition. Pi 1 goes to pi 1. If 2 goes to 2, then you also go to the first partition. If 2 goes to 3, you go into the second partition. If 2 goes to 4, okay. So it sort of seems like it's determined by where 2 goes. Okay. Acts on subsets of order 2 as follows. 1, 2 goes to 2, 3. 1, 3 goes to 2, 4. 1, 4 goes to... Right, so 1 goes to 2, 4 goes to 1. Okay. That looks reasonable. Looking at... It fixes pi 2. Okay. Right, so 1 goes to 2. 2 goes to 3. Okay, no, so 1, 3 goes to 2, 4. And 2, 4... Where's 2, 4? Goes to 1, 3. Okay, right. Okay, so this maps with pi 1. Ah, so he's... Okay, yeah. So 1, 2 goes to 2, 3, and then 2, 3... Yeah, and then 2, 3 goes to 3, 4, and then 1, 4. What does 1, 4 do? 1, 4... Yeah, 1, 4 goes to 1, 2. Okay, that makes sense. Okay, sure. Okay. If P and Q are elements of S4, the product PQ is the composed permutation, and the action is the composition of the actions. Yeah, so group action, this is another term, action. The composition of the action. So, okay, I don't see quite how that works, but oh, okay. So we have 3 things, and so he's saying we can define a permutation, or we can. How does it act on these 3 things? Okay. Ah, what? Is the composition... Okay. Okay, sure. Therefore, phi of PQ is phi of P. So phi is from permutations of S4 to okay, that makes sense. So we're mapping from permutations of 4 things to permutations of 3 things, and our map is determined by how does it permute these indices, and then how does that index permutation map to a permutation of these 3 partitions. Okay, that kind of makes sense. I would need to write that out a little bit more. Maybe this can go in a red star for write this out more. Red star. Let's make the red star 5 pointed. Okay, red star. Red star for write all of that out. Okay, because write starts with an R. And so does red. Therefore, the map is surjective, so its image is the whole. I don't see why this map is surjective. I don't see why. Why? Why? So its image is the whole group. Its kernel can be computed. Yeah, so this would fix the first permutation. This fixes the second permutation, and then, yeah, that one would fix the third permutation. Okay. Yeah, I don't, this argument, I'm sure this is correct. So this is surjective. What I would like to see what you would need to see is enumerate S3. That's not hard. Okay, so maybe this is an exercise. Enumerate S3. And then for each element, find a permutation of... See, I don't see how... I can understand why each of these elements is in the kernel. I don't see why why this is the entire kernel. How? So this kernel can be computed. How exactly? Or let me put that, let me highlight. Its kernel can be computed. How exactly? I like things that are like algorithmic and really clear. Okay, for each, find a permutation in how exactly? Okay, I'm just going to cross this out. Element in S4 that accomplishes it. Actually, yeah, you can just do that straight away. So let's say, okay. No, I think you would want to do enumeration. Okay, exercise enumerate S3. I might solve this and then put it in a document. Okay. Find a permutation of S4 that accomplishes the permutation in S3. Okay. That's about all. I'm sick of reading this, and this argument is just a big... What? See, I mean, this is sort of the essence of glowy math, is these weird, opaque arguments where you just kind of, it just throws a curveball at you, and you can like, if you really spend a lot of time dissecting it, it kind of makes sense. But all right, that's all I have for the moment. Thank you for watching. I'm going to do a Lingua Latina section because I've missed a bunch of days. I think what I might do is go back and rewatch my old videos first. Alright. Thank you. Bye.